All right, so today what we're going to do is we're going to take what we know about polynomial functions, what we've been working on the first half of Unit 1, and we're going to apply it to a rational function in behaviors and zeros. So exactly what we just did right there for a polynomial, but this time for a rational function. Any idea what a rational function is? It's not irrational then. Correct. All right. What would it look like in its form? All right, well, what about a rational number? What's a rational number? It's anything that can be written as a fraction. So a rational function is an algebraic fraction. Okay? Easiest way to talk about it is that it is an algebraic fraction. Okay? So that implies that it's a ratio between two polynomial functions. Right? It's a ratio or a quotient between two polynomial functions. You'll typically see it written something like this: R of x equals h of x over g of x. Just means we've got two polynomial functions there. The only stipulation is that g of x can't equal 0. What would happen if that bottom function was 0? It would be undefined, okay? Or your paper would explode, all right? One of the two. I'm not willing to risk it, to be honest with you. That's probably one of my favorite stories from my first few years of teaching. You don't hear this, Callie Beth, but all the education classes in college do nothing to prepare you for what it's really like in a classroom. Being in a classroom prepares you for the classroom. But my first year, I was bound and determined to do all these cute little things that they told us we needed to do that would make a difference. And one of those was I had kids fill out this excuse slip for why they didn't do their homework. It was back when I graded homework until I got smart. Anyway, and this one kid, God love him, he never did his homework. And so every day he would fill out his little piece of paper. Well, his excuses got better and better and better as the semester went along, okay? And the last one he ever turned into me, because this is when I quit doing them, he said, I divided by 0 and my paper exploded. And I was like, all right, that's it. I'm done with that. But it was really good. So now I just say that all the time. If you divide by 0, your paper will explode. I did give him a point for creativity because I thought it was pretty good. All right, so let's look at these ones that are down here below. Which one or do any of them represent a rational function? What do you think? We've got F, H, and we've got G. Is there anyone you could mark out for sure? Yeah, let's mark F out for sure. One, because it's not a fraction in any way, shape, or form, right? So we could definitely mark that one out. Okay. So then that leaves me H, and it leaves me G. What do you think? Okay, G is or is not? Is, okay. Why? All right, it does have a polynomial function in the numerator, and it does have a polynomial function in the denominator, okay? But let me ask you a question. Could I rewrite g of x like this? Is that the same thing? Yeah, okay. So that one's really not rational because that dividing by 3 is just a coefficient of 1/3. Okay, so that's what makes it not a fraction. I put that one on there on purpose, all right? So it's really easy to think, hey, that's a rational function. I've got a fraction. That must be it, right? But we have to be careful. If you have a constant in the denominator, it is not rational, okay? Which leaves me then with the only option of h of x. So 2 over 3x minus 1. Now, it'd be nice if all of our rational functions looked like that, but they don't. Yes? You could, but that 1 over 3x minus 1 is still a fraction. And it's algebraic in the denominator. Okay, what about this one? Two x plus 1 to the negative fifth power. Is that a fraction? Yeah, why? Okay, Jawak's doing the magic symbol. What's he saying we're going to do? Yeah, we're just going to move that 2x plus 1 to the denominator. This is going to be 1 over 2x plus 1 to the fifth power. So that does indeed make it rational, okay? Negative exponents, remember we fix those by dropping them to the denominator, all right? So remembering all the different things that we're going to do, right? So step number 1, can we identify a rational function? Now, I want to move into the end behavior, because end behavior of a rational function, and y'all, rational functions are kind of fun when you graph them, all right? They do all kinds of crazy things. They got arms and legs all over the place and squiggles in the middle and just all kinds of crazy stuff, right? But the thing about a rational function is that its end behavior is affected by the degree of each polynomial, okay? So it's affected by the degree of each polynomial and their leading coefficients. Okay. So each polynomial that we're going to have is going to have a degree, and it's going to affect my end behavior. Now, because we have multiple polynomial functions, we've got one in the numerator, one in the denominator, the polynomial with the greatest degree, okay, and I think this is a great word, all right, will have input values that dominate. Ooh. World domination. Okay, that dominate the rational function. Okay, so it's going to kind of take over. If you go back and listen to the videos, I didn't know this, but you hear me going tap, 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 the whole time I'm talking. It's funny. I got tickled the other night when I was listening to them play back. Okay, so we've got 3 cases in terms of our end behavior, okay, that we're going to talk about. These are also going to help us to understand asymptotes, horizontal asymptotes. So here's how it works. Okay, so let's say that the degree of the numerator equals the degree of the denominator. In other words, it might look something like this. F of x equals x squared plus 7x plus 2 over 2x squared minus 1. Okay, just made that up. All right, x squared plus 7x plus 2 over 2x squared minus 1. Okay, here's the great thing about it, right? The end behavior will approach Is it for me or Miss Sanders?
It's 204, that's all I saw.
Okay, well, it's not me. I wonder if it's 204A, which is next door. Here, y'all can come through here. Did you request a table?
Oh, okay, yeah, come on. Alrighty.
There you go.
Awesome.
Okay. Furniture delivery. Fun times. All right. You're good? No. The end behavior will approach the horizontal asymptote. Okay. The horizontal asymptote is the ratio between the leading coefficients. Okay. Okay, so HA stands for horizontal asymptote. All right. So our end behavior will approach our horizontal asymptote. How do we get that? It's just the ratio of those leading coefficients, all right, from the numerator and the denominator. Okay, so if we look at that example, okay, my horizontal asymptote is going to be y equals, what's the leading coefficient of the numerator? 1. And the leading coefficient of the denominator? 2. So my horizontal asymptote is y equals 1/2. And so my end behavior, when we get to limit notation here in just a second, is that the function's going to approach 1/2 as x approaches positive and negative infinity. Okay? So our function's going to approach that horizontal asymptote as long as the numerator equals, the degree of the numerator equals the degree of the denominator. Okay, good. Those are the best kind. Okay, so case 1. All right, case 2. The degree of the denominator is greater than the degree of the numerator. So that might look something like this. F of x equals x plus 2 over 3x squared minus 1. Okay, x plus 2 over 3x squared minus 1. The degree of the denominator is 2x squared. The degree of the numerator is 1x. Okay, x plus 2. So this one is kind of interesting because I want you to think about this for just a second. If we took those leading coefficients, if we took those leading degree terms only, right? You don't have to write this down. But x over 3x squared, algebraically, what does that reduce to? 1 over 3x, okay? And I want you to think about what would happen if I put infinity in there for x, okay? So I can't think of infinity, but let's say I do 1 over 3 times 1,000, okay? That's 1 over 3,000. What is that getting closer and closer to? 0, okay? So the bigger number I put in there for x, it gets closer and closer to 0. So anytime that we have the case where the denominator is a degree or is higher degree than the numerator, our end behavior will approach the horizontal asymptote y equals 0. Always, okay? Always, y equals 0. It is your horizontal asymptote, okay? All right, so case 3, when we're talking about end behavior. So we're either going to approach a horizontal asymptote that has some kind of numerical value. We find that when the degree is the same on the top and bottom, we just do the ratio of those leading coefficients. It's going to approach 0, the horizontal asymptote is 0, if the degree of the denominator is bigger. Well, what happens when the degree of the numerator is bigger? All right, so take a look, something like this. Oh, I messed up my pattern. Hold on, I got to go back to black. Okay. F of x is equal to x cubed plus 7 over x minus 1. Okay. X cubed plus 7 over x minus 1. Right. So again, I want us to think about taking just those leading degree terms, those leading terms for just a second. Okay, again, don't write this down, but if I took x cubed over x, what would that reduce to? X squared, okay? Here's the really cool thing. What does x squared look like? It looks like a parabola, okay? What's its end behavior? It's up on both sides, right? Here's the great thing. If the numerator is larger than the denominator, then the end behavior will mirror the polynomial of the resulting quotient. Okay, so my end behavior will mirror whatever's happening to this leading term quotient, all right? What does it do? Well, that polynomial, all right, x squared goes up and up, all right, approaches positive infinity both ways. So this rational function in the end would do the same thing, okay? It's kind of neat how that all poses. It's this concept of dominance, all right? And what happens, okay? Now, I want to talk about a special case right here within case 3. You've heard of horizontal asymptotes, you've heard of vertical asymptotes, but we can also have what's called a slant asymptote, all right? Slant, you'll also see it referred to as oblique, all right? An oblique asymptote. What do you think that means? You have an asymptote that's slant or oblique. Okay, it's going to be linear, all right, and it's going to follow slope-intercept form, okay? So a slant asymptote is going to have that form, y equals mx plus b. It's going to be this diagonal line that guides our function, especially around its end behavior, okay? Now, how do we find it, or when do we know when it occurs? Well, here's the great thing. It only happens when the degree of the numerator is exactly 1 more. I'm going to say 1 greater than the degree of the denominator. Okay, so a slant asymptote only occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. Okay. And it'll have that form, y equals mx plus b. It'll have a slope and possibly an intercept. It could intercept it at 0, all right? But it'll have that linear function, all right? All right, so let's look at these next 3, okay? We want to determine, does the following rational functions have a horizontal asymptote, a slant asymptote, or neither, all right? If it has a horizontal asymptote, then we want to write the equation of that horizontal asymptote. So using those 3 cases, all right, that we just talked about, all right? Let's look at the first one, all right? We're going to look at those leading terms. We're talking about the degree. What's true about the leading terms in the numerator and denominator for the first one? They're the same. So because they're the same, do we have a horizontal asymptote? We do, okay? Our horizontal asymptote is the ratio of the coefficients. So what would that ratio be? 3/5. When you write horizontal asymptote, it is a linear equation. Put y equals. If you don't, you won't get credit, right? It's one of those little tedious things good mathematicians do, all right? It's a horizontal line, so we want to be sure and put y equals there, okay? That's important, all right? Look at B, all right? Y equals 2x minus 5 over x squared plus 3x. Let's take a look at our leading terms, all right? So I have 2x and an x squared. Who's larger? The denominator. When the denominator is larger, we have a horizontal asymptote. Okay, what is it? Y equals 0, always. Okay, if the denominator is larger, we have a horizontal asymptote, and it is y equals 0. Okay. And then finally, take a look at C. All right. Looking at your highest degree terms, who's larger, numerator or denominator? Numerator. So if numerator is larger, there's no horizontal asymptote. In order for there to be a slant asymptote, the degree has to be exactly 1 greater. All right. Is it exactly 1 greater on the top? Yes. So we have a slant asymptote. Okay. Now, you will learn Monday how to find a slant asymptote. Okay. So for right now, it's good enough to know that we got one. All right. And remember, asymptote only has 1 S in it. Okay, not 2. All right. I tried to say that one time. I tried to say there's only 1 S in asymptote, but I said there's only 1 in asymptote. It was not good. We weren't able to function much longer after that. But it's all good. All right. Okay, so now we can identify them. Let's talk about our limit statements. All right. Again, when we're talking about in behavior, we're talking about limits as x approach infinity and negative infinity. So that doesn't change. All right. What we have to know is, do I have a horizontal asymptote so that I can talk about that behavior? Do I have a degree that's different so that we can talk about that behavior of what's left? Okay. So here we go. When we start, I'm going to do one with you, then I'm going to let you practice. All right. Let's do the middle one. Okay. Then I'll let you guys practice the 2 on the ends. So we want to know the end behavior. So on the left, it's going to be the limit as x approaches negative infinity of g of x. And then from the right, the limit as x approaches positive infinity of g of x. Okay, so my statements will start the same, all right, for all of them. What we have to figure out is, well, what's happening, all right? Do we have a horizontal asymptote in this situation? What do you think? All right, is there a horizontal asymptote? Okay, so if we look at it, where's the largest degree? Denominator. So what's my asymptote? 0. So my end behavior approaches 0. Okay. All right, you try A and C for me real fast. Did. So on the first one, again, we're doing those limit statements, so that's not going to change. For the left, limit as x approaches negative infinity of f of x. And then limit as x approaches positive infinity of f of x. So we just need to know, do we have a horizontal asymptote? What do you think? Yeah, I think so too. What's true about the 2 degrees? They're equal, so we just do the ratio of the coefficients, and what would that give me? 1/2/6, which is 1/3. So my end behavior statements, they both approach 1/3. They approach that asymptote. Okay, did you get it? Get it? Got it good? All right, I love the last one though. Tricky, tricky. It's tricky to rock. Okay. Okay. Did y'all know there's a group called the Butthole Surfers? Do y'all know this? Yes, it is. Okay, so my husband and I went on a trip, just the 2 of us, and he said, I'm just going to randomly shuffle my playlist in my phone. I'm like, okay. So, I mean, there was more music than we could listen to in a week. Okay, so anyway, we're coming down the road. He's singing every word, and I'm like, what is this? And it said Butthole Surfers, and I was like, that's a lie. You made that up. He's like, no, apparently there is. God love him. Okay. Parker, he'll be happy to know that you knew who that was. I'll let him know. He'll be impressed. Okay, so let's look at this one. Horizontal asymptote on this one. Yes, no, maybe not. No. Okay. It's a slant. Look at y'all. It's a slant. Asymptote. But let's think about what's going to happen. All right. What kind of slant is it going to have? I'm so impressed. Right. Think about this. If I took 3x to the fourth or negative 3x to the fourth over x cubed, what would I be left with? Negative 3x. Okay. So I'd have a line with negative slope. Okay. And when that happens, my end behavior follows the behavior of that resulting function. Okay. So on the left-hand side, so if I'm thinking about y equals negative 3x, it would look something like this. What's it going to do on the left-hand side? Where's it going to point? Positive infinity. And where's it going to point on the right-hand side? Negative infinity. And that's how we get those values. Okay? So you got to think about that function that would be left over if we reduced. All right? If it's linear, especially if it's got a negative coefficient, all right, what would a linear function do in terms of all of that? Okay? All right, do D and E for me real fast. Y'all can do those. It's just pictures. Those are my favorite. All right. What are we approaching on D? We're approaching 2, okay? We're approaching that line that we have there as we get closer and closer to 2, all right, both ways. And then what about on E? -1, okay? We get -1. So just looking at it graphically. Question about those two, okay? All right, good. Well, let's get into the good stuff. The next part's super easy, zeros of rational functions, okay? How do you make a fraction equal 0? Which part of it has to equal 0? The numerator, okay? The numerator. If you want a fraction to equal 0, then the numerator has to equal 0. But as with all things algebra, there's always a but, it feels like, okay? So zeros of our rational functions are where the numerator equals 0. Okay, as long as the numerator and denominator do not share factors. Okay, so we find zeros of a rational function where the numerator is equal to 0 as long as the numerator and denominator do not share factors. Okay, that creates something called a whole, and we'll learn more about that in the next lesson. Okay. Not in trouble. Okay. So let's take a look at a couple of examples here, see if we can find the zeros of this function. These functions, one of the things, if we don't want them to share factors, what are we going to have to do to our numerator and denominator? Factor. Okay? We're going to have to factor. If we want to make sure they don't share anything, then we're going to have to factor. Good news is on the bottom one here, trinomial, the first one, that would be what? X minus 9, x plus 5. Does it share anything with the numerator? No. So my 0 is going to be where 2x minus 3 is equal to 0. Well, that would be at 3 over 2. Okay, so we just look at the numerator. We don't think about the denominator. Right? So always factor first. If you have something, excuse me, that matches from numerator to denominator, we don't include it as a 0. Okay, it's something else. And we'll talk about that, like I said, in a day or two. Let's look at the next one. Go ahead.
So the zeros from the denominator don't count as
The,
zero?
nope. No, only the numerator. Yeah, only the numerator. Because if you want a fraction to equal 0, the denominator can't equal 0. Okay, that makes sense? Okay. All right. Now let's take a look at that next one. Definitely going to need to factor on this one. X squared minus 4, what's that going to factor into? Good, x plus 2, x minus 2. And then my denominator, x minus 3, x plus 2. Okay, so is there a factor that they share? Yes, so I'm not going to include that one. I'm just going to mark it off. Okay, not going to include it. I'm only going to look at the numerator. What's the only factor I have left in the numerator? X minus 2. So my 0 is where that equals 0, or at positive 2. Okay, so zeros in the numerator. All right, so in behavior of rational functions, all the horizontal asymptote stuff's in there, zeros. Questions about any of that? All right, let's do inequalities. Okay, rational inequalities are a little bit more involved. Okay, they're going to require a little bit of thinking on your part, but it's not terrible. All right, so when we solve a rational inequality, all right, it is a little bit more involved, and here are some helpful hints, all right, things that can help you along the way. Be sure it's got 0 on the other side, all right? If it doesn't, then we've got to rearrange, get like common denominator. You get your steps when you sit right there. Okay, we want to make sure we have a single rational function, meaning I don't have like x over x plus 1 plus 7 over x minus 2, right? We want a single rational function, all right? And then this is what's a little bit different, okay? We're going to do something called a sign chart, right? And this time we're going to look at where the numerator and the denominator equal 0, all right? So that's different. So we're going to look at numerator and denominator. Right? So we're going to find zeros of each, right? Okay. Once we find those values, I actually like to mark the zeros of the function so that I know where they are, not the undefined pieces, because the only places that we're going to include values are where they are equal to 0, like what are the real zeros, okay? So I changed that a little bit, and then we use the sign chart. I'm going to show you how that works, and we look for where something's positive or negative. Positive meaning greater than 0, negative meaning less than 0, right? So we're going to test values. This is all can be done without a calculator, okay? We're looking at positives and negatives, and we'll kind of walk you through my thinking on this. This will show up again later in this unit, so it's something we need to get a good handle on, okay? And then we'll write our answer in interval notation, all right? So let's take a look at some. Right now, those steps probably sound hideous and don't make any sense whatsoever. Let me walk you through one, okay? So let's look at this first one together, all right? We want to solve that inequality. We want to know where x minus 2 over x plus 6 times x minus 3 is greater than or equal to 0. So are we looking for positives or negatives? Positives, because we're greater than or equal to 0. So here's what we're going to do first. Let's find the real zeros of the function, okay? So the real zeros of the function, do they come from the numerator or the denominator? Numerator. And so the real zero of this function is going to be x equals what? 2. Okay? The next thing we want to do is we want to find where is the denominator equal to 0. They are not zeros of the function. We just want to know where they are. All right? So in our denominator, what are other values we're going to consider? We're going to consider -6 and 3. Okay? So on your sign chart, here's what you're going to do. Right? We know this function goes on forever. We're going to list those numbers that we just found in order. Right? So I'm going to do -6. I'm going to then do 2, and I'm going to mark 2 in black so that I know that it is actually the real 0. Okay? I did red, so those are no-nos. Okay? Don't tell somebody you did no points. That would be weird. Okay. And then 3. All right. I have a lot of sayings that you cannot write in an explanation, all right, on an AP exam. But they help me remember. Okay. All right. So now, this is the tricky part. Okay. What we're going to do is we're going to pick a number that's to the left of -6. Right? It doesn't have to be close, but, you know, just left of -6. So, okay, I'm going to think about -7. All right? And what I'm going to do is I'm going to go up here to my function, and I'm going to think about the sign I would get if I plugged in -7 into each parenthesis. Okay? So, on the top, -7 minus 2, would that be a positive or a negative? It'd be a negative. I don't care about the exact value. Okay? On the bottom, -7 plus 6. That's a negative. -7 minus 3. A negative. Okay? So here are the signs in my fraction. I have a negative on the top and a negative times a negative on the bottom. What's a negative times a negative on the bottom? It's really a positive. And what's a negative divided by a positive? It's a negative. So this is my sign for when I am to the left of -6. I would have a negative number there. Okay? So we're just thinking about what would be the sign of the answer. What would be a good number to choose between -6 and 2 that might be really easy to operate with? 0. He's my favorite number. Okay? So I'm going to put a 0 in. Let's repeat that process. Put it into our fraction. 0 minus 2, positive or negative? Negative. 0 plus 6. Positive. 0 minus 3, negative. So I have a negative divided by a negative, which is a positive. Now, do not assume aside that these always alternate. Okay? You have to check them. All right? 9 times out of 10, they're going to alternate. But there's going to be that one time that it doesn't, and you'll miss it. Okay? What's the number between 2 and 3? Uh-oh.
2.5.
2.5, okay? Don't panic over a 2.5, okay? Because I'm not doing a physical numerical calculation. I'm thinking about signs, okay? So on the top, 2.5 minus 2, positive or negative? Positive. 2.5 plus 6. 2.5 minus 3. Negative. So I end up with a positive divided by a negative, which would give me a negative. You see what I'm doing? Okay, that's called a sign chart. All right, let's do one more. And I wish I could tell you there's an easier way to do it, but there's really not. Okay, what's bigger than 3? 4. All right, and let's look at our signs. Okay, 4 minus 2. 4 plus 6. 4 minus 3. Positive divided by 2 positives is a positive. Okay. So now here we've got our signs, all right? Now this is where we use our sign chart, we interpret it to answer our question, all right? Now, you may be able to fill in the sign chart without having to do this in the green bubble. Like you can think about it and write it down. That's fine, okay? I tend to write it down because I make numerical errors, all right? Because my brain lies to me from time to time, okay? Now let's answer our question. What's my solution? I want to know what are the places where my sign chart is positive, where it's greater than 0. So here's what we're going to look. That happens between -6. Okay, -6 was a no-no because it's in red, so I use a parenthesis. But 2, because I had a bar on that inequality, I'm going to put a bracket around it. Okay, and it's really a 0. Okay, it's equal to 0 right there. Then my second interval, where it's positive, starts at 3. 3 is a no-no. And it goes forever, so positive infinity. That is the solution to my inequality. That was a lot. So take a second and digest it. Ask me a question. Camera 1, camera 2. Camera 1, camera 2. Okay. Wayne's World, great movie. Okay, all right. Dodgeball is one of our other favorite movies. We watched that this weekend. If you can dodge a car, you can dodge a ball. Okay. All right. Let's do the next one. Okay. I promise, the more of these you do, the better you get at them. Okay. First thing we need to do is to factor, all right, so that we can find our zeros, we can find all the things that we need. What would that numerator factor into? Good. What about the denominator? All right, x minus 5, or x minus 5 squared. All right, so let's think about our zeros. All right, where's it going to be equal to 0, the whole function? Yeah, positive and -2. All right, they come up there at the top. What are our no-no points or no-no point? Yeah, it would just be 5 because that would be x minus 5, x minus 5. Okay, so at x equals 5. All right, now here's the crazy part about this one. Look at your inequality. Does it have a bar on it? No, so everything's a no-no point. Okay, doesn't matter. If it doesn't have an equal sign, I don't care about where it's really equal to 0. All right, we're not going to do that. We're not going to equal anything. And if we're not going to equal anything, everything's a parenthesis. Okay, so when I set up my sign chart, all right, we would start at -2, +2, and then +5. All right. Now, I'm going to save you a little bit of time on this one. Is it going to matter what I plug in to the denominator because I'm going to square it? Does that matter? What's the square going to do to anything I put in there? It's going to always be positive, okay? So regardless of what number I put in that denominator, it's going to always be positive because I'm going to square it, all right? Negative times a negative is a positive times a positive is a positive. Okay, so when we check our signs, all right, when we check our signs, let's try -3. I know the denominator's positive. I only have to really check the top. Okay, -3 plus 2 would be a negative. -3 minus 2 would be a negative. Well, that would be a positive divided by a positive, which is a positive. Okay. Check my next interval. Ooh, I can use a 0 right there. He's my favorite. Okay, I know the denominator is going to be positive, so I don't have to think about it. On the top, I'm going to get a positive and a negative. If I finish that ratio, I'd get a negative. All right. 2 to 5, I might pick 3. No, my denominator is going to be positive because it's squared. All right. 3 plus 2 would be a positive. 3 minus 2 would be a positive. I would get a positive. And then I might pick 6. No, I'm going to get a positive on the bottom. 6 plus 2 is positive. 6 minus 2 is positive. Look at there. There's one of those places where it doesn't change signs. Okay? So it stayed positive. right? Now, let's find our solution, okay? Our solution is where that rational expression is less than 0. So does that mean I want the positive intervals or the negative intervals? The negative intervals. There's only one of them, and where does it happen? Between -2 and +2. Because we're not equal, we're going to use parentheses on everything. Okay? I want you to try this one right here by yourself. Okay, just for sake of time, we're not going to probably do them all, but I want you to try that one that I put the purple star next to. See if you can solve that one. First thing we need for sure are the actual zeros of the function, okay? You could factor that numerator if you want to, if it makes it easier for you, and write that as 4 times x plus 2 over x plus 5 is less than or equal to 0. That's perfectly legal, okay? It does make it easy to see what our 0 is, our real 0 of that function is at x equals -2. And then what's my no-no spot? -5, okay? And so when we set up our number line, we've got -5 and then -2, okay? So factored form allows me to be able to do that testing points really quickly, okay, using the parentheses. So less than -5, I might choose -6. So on the top, that would give me 4 is always positive, so that's irrelevant. -6 plus 2 would give me a negative. -6 plus 5 would give me a negative. So in this first interval, I have a positive. Okay. Between -5 and -2, we might test like a -3. Okay. -3 plus 2 would be a negative. -3 plus 5 would be a positive. Negative divided by a positive is a negative. Okay. And then we might check greater than -2. We can choose 0, my favorite friend. Okay. 0 plus 2 would be a positive. 0 plus 5 would be a positive. And so we get a positive. Okay. So now the question becomes, what's my solution? Well, which one of those intervals are we interested in? Well, we're looking at the one where it's less than or equal to 0. Okay. The only place it can be equal is at -2. Okay, which would include a bracket instead of a parenthesis. So because it's less than, do I want positive or negatives? Negative. I want negatives. And so my negatives happen between -5 and -2, but I'll include that -2 because it is my 0.
So the -5 won't have a bracket?
No. Okay, because anytime it's one of your no-no spots, if it comes from the denominator, we cannot include it ever. Okay, good question. All right. Yeah. Okay. You okay? You good? So let's do this. I want to jump down and look at a graphical one. If you'll go over to the next page, right? I want us to look at this graphical one, and then we might go back and do the one up at the top, but I want to be sure we get the graphical one before we leave. Okay? So here's one where they've given me a rational function as a graph, all right? And they want me to look at it graphically and find where it's greater than or equal to 0, or less than or equal to 0, greater than 0, and greater than or equal to 1, all right? So that being said, one of the things that's important is that I find the zeros of this function. How am I going to find the zeros? Just looking at it. Yeah, where it crosses the x-axis. How many times does it cross the x-axis? Twice. Okay. So there are my actual zeros. Any other numbers that I use, okay, if it says equal to, we'll have parentheses around them. Okay. Now, it wants me to find where is this picture less than or equal to 0. Well, by 0, it means the x-axis. Okay. So we're looking for where is this picture below the x-axis? All right, where is it below the x-axis? Well, we've got to come into and consider, all right, these asymptotes, all right? This vertical asymptote happens when x is equal to -3, and this one is at where x is +3, okay? Vertical asymptotes, we can't cross them, we just get really close to them. And so if we look at where this graph is below the x-axis, well, it's right here, and it's right there, okay? That's where it's below. Well, how would we write those intervals? Because it also says equal, we will include that 0, okay? So remember, you read a graph from left to right. And so if I'm coming from the left, that asymptote starts at -3. And then I'm below the axis until x is -1, but I'm actually equal to 0 right there, so I'm going to include it. All right. And then the next part, all right, I'm below the axis again, starting at 2. And then I stop when I get to that asymptote, which is 3. I can't include it, so I put a parenthesis there. Listen, y'all gonna have to pay the wrath to Callie of having to go tinker. Okay. See why I want a Ring doorbell? Where I can open the door and be like, it'll be nice. Okay. Let people come in. Don't let people come in.
I don't think you'll have to do that.
I know, it'd be nice though, wouldn't it? Okay. I got a husband who's pretty crafty. I think he could make it happen. All right. So we're just looking at the picture, looking for where it was less than or equal to 0. Let's look at the second one. This time I want to know where is the function greater than 0. In other words, where is it above the x-axis? Well, it's above here, this little bitty piece, and here. Okay, so we've got to label those intervals. Notice there's no bar on that inequality, so we will not put a bracket anywhere. Okay, we won't put a bracket anywhere. So if we go in here and we name it, to the left, we're starting at -infinity, and we're going to go up until x is what? -3. Okay. Then we're going to do that little bitty piece in the middle. Okay, -1 to +2. All right. And then that last piece starts where? At 3, and it goes until infinity, and that's it. Okay. So writing our inequality from there. Yes.
I'm just confused on the brackets, like where to put them.
Okay, the only time we include a bracket is at a 0 if the inequality has a bar,
What's that?
because the bar means or equal to. Okay, so the bar means or equal to 0, and that's where that function's equal to 0, is at those x-intercepts.
Wait, what does the V mean?
Oh, it's a U, means union.
Oh, yeah.
Okay, or you can just use and. You can use an and symbol. You know, just and is fine. Right? All right, last one. This time they shift it. Okay, where is this function greater than or equal to 1? All right? In other words, whoo, got excited. All right? Where is it above that line? Okay. How many places does it happen? Twice. Do we have any zeros in that place? No, so everything's a bracket again. I mean, everything's a parenthesis again. Okay. So when we write our solution, okay, we're talking about negative, oh, farfignugan. All right. -infinity to -3, and then 3 to +infinity. So looking at it graphically. Okay, looking at it graphically. The only time we'd use a bracket is at an x-intercept if the inequality has a bar. All right, so that might be a note you want to make to yourself so you don't forget that. Everything else is a parenthesis. Okay, so tomorrow, all right, you're going to get your practice, your lesson practice. Now, I know some of you, you're like, I need to practice a little bit tonight, okay? If that's you, okay, we're going to do all the problems that are on the two worksheets for tomorrow. And if you notice, I've got it all up there, what you're going to do over the days that I'm gone, okay, on the sideboard instead of putting your standards.